This is the last part of this short course on array processing, and it focuses a bit on the concept of array gain. We have already introduced, but I want to say more. So, I mean, we defined the array gain, if you remember, and according to the definition that we gave, the array gain is the ratio between the signal to noise. When I say signal to noise, I intend any kind of noise disturbance. So it can be thermal noise, clutter, interference, so everything. So signal to noise ratio at the output of the beamformer divided by the signal to noise ratio at the input. So in other words, the array gain, it's a parameter that tells you how much we can improve the signal to noise ratio going from the input to the output of the beamformer. So how much we can improve the signal to noise ratio thanks to spatial filtering. And this is very important, and clearly the array gain depends on a number of factors, and in particular depends on the distribution in angle of the disturbance, and depends on the geometry of the array. And roughly speaking, you will see that is proportional to the aperture of the array. So in general, the larger is the array aperture, so the larger is the number of sensors, and the greater is the array gain. So in general, when you increase the size of the array, ideally, then obviously there are problems with the implementation, calibration, etc. But typically, when you increase the size of the array, you improve the signal to noise ratio at the output because you improve the array gain, and you improve the resolution, if you remember. Obviously, to increase the size of the array means that you have to put more money. So the cost of the hardware increases. Now, let's first derive the array gain of the wideband delay and sum beamformer. As I told you, as I anticipated, is the same as the classical beamformer, basically. So we start from the expression of the signal received at time n at the M sensor. So we have the signal received at the reference sensor delayed by delta M plus noise. So the input signal to noise ratio is the instantaneous power of the signal of interest X divided by the instantaneous power of the noise. Now, let's assume that the noise is stationary both in time and space. So the power of the noise does not depend on N and M, it is a constant. And the same for X. So let's assume that this is the power of the input signal. So the input signal to noise ratio is the power of X divided by the power of noise. The output of the beamformer is given by this expression, and I assume that the weighting is uniform, so there is no shading. So I'm talking about the plain delay and sum beamformer. So the expression of the output, I mean, this is a linear transformation Basically, this is an FIR filter with impulse response of length m equal to over m, so with rectangular impulse response. So the filter is linear. So at the output, we have the superposition of the signal component plus noise. So we have just derived this result 1 hour ago. So the power of the signal is the same. So the power of the signal is the same as the output. So in other words, the signal passes undistorted through the beamformer. So it's a sort of distortionless constraint. What about the noise? The power of the noise is the power of this Wn. So we have to calculate the power of this term. Now, we can bring 1 over m outside, so we have the square, so we have 1 over m squared. And so we have the expectation of the sum. If the noise samples are spatially uncorrelated, they are also zero mean. So basically what we want to calculate is the expectation of the sum squared. So we want to calculate the variance of the sum. But if the different terms of the sum are uncorrelated, the variance of the sum is equal to the sum of the variances, because all the cross terms are equal to 0 because they are uncorrelated. So I repeat, the expectation of the sum square is equal to the sum of the expectation of the square of the sample. This is because when you calculate the square, the expectation of all cross terms is equal to 0. Now, because we said that the noise is stationary in time and space, each term in this summation is equal to sigma w squared. So you will sum m times sigma w squared, and so we get m sigma w squared divided by m squared, so we have sigma w squared divided by m. This is the well-known mean square error of the sample mean estimator. So if you are familiar with sample mean, with the property of the sample mean estimator, it's an unbiased and consistent estimate of the mean, and the mean square error is the power of the noise divided by the number of samples in the average. So the output signal to noise ratio is sigma x squared divided by sigma w squared divided by m. Now, sigma x squared divided by sigma w squared is the input signal to noise ratio, and so this term here is exactly the array gain. So the array gain of the delay and sum beamformer, if the noise is partially white, is exactly equal to the number of sensors. You should not be surprised, because this is exactly the processing gain of the matched filter in white noise. So if you are familiar with the properties of the matched filter, the improvement factor or processing gain, so the improvement signal to noise ratio, the output of the matched filter, is exactly equal to the size of the filter. And in this case, the delay and sum beamformer, which is equivalent to the classical beamformer, which is nothing but a matched filter, in white noise, the processing gain, and because we are talking about spatial processing, the processing gain is called array gain, and there is no surprise that it is equal to the size of the filter, which is equal to the number of sensors. So the array gain of the delay and sum beamformer in spatial white noise is equal to the number of sensors. So you can increase the array gain by increasing the number of sensors. And I mean, this is true whatever is the geometry of the array. So we don't make any assumption about the geometry. So it's true for any geometry of the array. Now, what happens if the samples are spatially correlated? So let's consider the different samples in the sum. So in this sum, we have different values of m. So we put in a vector, so w1, w2, wn. The argument is n minus the delay, which is epsilon 0 minus delta 1, epsilon 0 minus delta 2, and so on. Remember, the value of delta is chosen depending on the steering direction. So if you express the mean of these samples in vector notation, so what we calculate is this summation here. So it is 1 over m summation of the noise samples. The summation goes from m equal to 1 to capital M. We can express this summation by using vector notation. So if 1 is the vector of all ones, so it contains all ones, we can express the summation as the inner product between the vector 1 and W. And then we have 1 over m in front of it. And the power of the noise is the expectation of the noise at the output of the beamformer square. Now, this square can be written in the following way. This term that multiplies its Hermitian. Now, let's assume that the noise is correlated. So the spatial correlation matrix of the noise RW is the noise power that multiplies the matrix, the normalized spatial covariance matrix. So it's a matrix that contains all the correlation coefficient between the noise at different sensors at the same time. And by definition, all the elements of the main diagonal are equal to 1. So we calculate the Hermitian, we bring the one vector, which is deterministic, outside the expectation. The expectation operates on what is random, that is the W Hermitian. By definition, this is the spatial correction matrix of the noise at time n. Because the noise is temporally stationary, the result of the expectation does not depend on n, and it is sigma W squared times Q. And then you have on one side 1 Hermitian, on the other side 1. So this is the result. This is the power of the noise. So the signal to noise ratio at the output is this quantity, is sigma W squared divided by this. So you divide the output signal to noise ratio by the signal to noise ratio of the input, and so what you get is m squared divided 1 Hermitian Q1. Now, if you put in evidence m, which is the array gain in white noise, so you can say that if the noise is correlated, the array gain is the array gain in white noise multiplied by this term. Now, this term is what? When you calculate 1 Hermitian Q1, if you think about 1 is a vector of all ones, the result of this multiplication of 1, so this denominator is just the sum of all elements in the matrix Q. So if Q is the identity matrix, so if the noise is white, the result of this double summation is m, and this ratio is 1, and so you get m. if the noise is correlated, typically the correlation is positive, the sum of all elements in this matrix is greater than m. So this ratio is smaller than 1. And so the array gain in correlated noise is smaller than m. So it is smaller than the array gain in white noise. So if the noise is correlated, the array gain that we can achieve is smaller. So the most favorable scenario is the scenario where the noise is white. If it is correlated, and typically the correlation is positive, the array gain that we can achieve is smaller than m. Okay. Now, so this is the delay and sampling formula. So let's consider now two quadrature beamformer, the classical beamformer and the optimal clairvoyant beamformer. And let's compare the two in terms of array gain. Then we will see some numerical results. So in the case of narrowband signal, the complex envelope of the snapshot received at time n, so the temporal snapshot at the output of the array, if there is only one single point light source, so we have the array response calculated at the angle of arrival of the source multiplied by the complex envelope of the signal generated by the source plus disturbance. And I repeat, disturbance can be clutter, thermal noise, interference. So what is by definition the input signal to noise ratio? Now the input is a vector. So the signal to noise ratio is typically defined in this way. We take the signal vector, we calculate the energy of this vector, so the sum of the element square. So the energy is the Euclidean norm square. So this symbol is the Euclidean norm square. So it's the sum of the elements of this vector square. Then, if there is something random, we have to calculate the average, so the statistical average of this quantity. The same at the denominator for the noise. So we take the noise vector, we calculate the energy, and then we take the expectation. So this is the typical definition of signal to noise ratio for the array output vector. Now, the Euclidean norm square can be written as the vector Hermitian times the vector. So it is the summation of the elements of this vector modulo square. And then we take the expectation. Now, the result of the expectation we have already calculated is m times the noise power. The numerator, again, we have the Hermitian times this. So we have A Hermitian A that multiplies S conjugated, it's a scalar, so the Hermitian is just a conjugate that multiplies S of n. So S of n modulo square. Now, A Hermitian A is deterministic, so we bring outside. The expectation of S of n modulo square is the power of the signal. And so A Hermitian A is equal to m, because it's the energy of vector A, which is 1 plus 1 plus 1 m times. And so m divided by m is 1. And so the input signal to noise ratio is sigma s squared divided by sigma w squared. Then we have the beamformer output. The beamformer output for a generic beamformer is H Hermitian Y. So we have the signal component at the output plus the noise component. The signal to noise ratio is the instantaneous power of the signal component divided by the instantaneous power of the noise component. Now we don't put the Euclidean norm because the output is a scalar. So we take just the modulo square of the two terms. So we have numerator and denominator. The numerator is the modulo square of this one. This is deterministic, we bring outside. Then the expectation S of n modulo square is sigma s squared, the power of S. So this is the numerator. And the denominator, we calculate the modulo square as this quantity multiplied by its Hermitian. And again, we bring outside the expectation H Hermitian and H because they are deterministic. The expectation of W Hermitian is the correlation, spatial correlation matrix of the noise, which is sigma W squared times Q. And so this is the output signal to noise ratio for a generic beamformer H. These two terms, the ratio of these two terms is the input signal to noise ratio. So we can say that for a generic beamformer H, this is the expression of the array gain. So this is the expression of the array gain. Then, if we choose the classical beamformer, the classical beamformer, as you remember, is a matched filter. So it's proportional to the array response calculated at the directional arrival of the source. So if you make this replacement, so we plug here 1 over m a in place of h. We simplify whatever we need to simplify, and what we get is m squared divided by a Hermitian q a. So this denominator, if you want, can be written as trace of q a Hermitian. So you can write in this way, or you can write in this way. Now, this is the general expression of the array gain of the classical beamformer if the noise is partially correlated. If the noise is white, the normalized spatial covariance matrix Q is the identity matrix. And if Q is the identity matrix, the denominator is equal to M, and this ratio, as we know, is equal to M. So as I said, the array gain of the classical beamformer in white, spatially white noise is exactly the same as the array gain of the delay in some beamformer in white noise. And it is exactly equal to the number of sensors. So for example, in the case of the so-called isotropic noise, so the noise comes with the same density from any direction. The structure, it can be proved that the structure of the normalized spatial covariance matrix is a sinc function. And so the value of the element of Q depends on the choice for D over lambda. So this is a known result. So I will report this fact without proof. You can find on books. if the array is EULA, this is the structure of the array response. And so you can calculate for a specific array geometry, for example, EULA geometry, you can calculate the array gain. And if the noise is correlated, the array gain depends on the correlation, because it depends on the shape of Q, and depends on the steering direction. So it may change if you change the steering direction theta t. If the noise is partially white, Q is the identity matrix, and this ratio is M. So it does not depend anymore on theta t. Now, when the isotropic noise is partially white, if you look at this expression, this happens only if the distance between the element of the Euler array are spaced by lambda over 2. Because if d over lambda is 0.5, 2d over lambda is equal to 1, and the sink of m minus k is different from 0 only for m equal to k. So basically, if d over lambda is 0.5, Q becomes equal to the identity matrix. So, but only if you sample in space at lambda divided by 2 intervals. If you choose a different spatial sampling interval, so if you choose a different value for d over lambda, different from 0.5, Q is no more the identity matrix. And so the isotropic noise generates spatially white noise only for this sampling interval, only if d over lambda is 0.5. So be careful. Otherwise, the array gain can be calculated. So you can express the denominator as a double sum. You can use the double sum formula. You can simplify. But anyway, it's not a difficult calculation. At the end, you find this expression, and this expression can be very easily calculated in MATLAB. I will show you some numerical results. Okay. So this is the array gain of the classical beamformer for isotropic noise. And you can see that if d over lambda is different from 0.5, it depends obviously on the value of d over lambda. It depends on m, but it also depends on the steering direction. Actually, if you are familiar with antenna design for isotropic noise and planar wave, the array gain coincides with what has been defined as directivity index. So they are slightly different things that coincide when the noise field is isotropic and planar. And if you look at this expression, you can see that when d over lambda is smaller, the value of the sink of this quantity is greater. So the denominator is greater, and this ratio is smaller. So in other words, at low frequencies, so high wavelength, d over lambda is small, the values of the sink are greater, so the noise correlation increases, and as a consequence, the array gain decreases. So the array gain decreases with the frequency. The higher the frequency, and the higher is the array gain. These are some figure where in the figure on the left, I plot the array gain for two different values of d over lambda. If d over lambda is 0.5, as I told you, the array gain is m. So for example, if m is 20, and you plot the array gain in dB, so it is 10 log in base 10 of 20, about 13. So you have a constant value 13. If d over lambda is different from 0.5, the array gain depends also on theta t, and it changes with theta t. And in this case, for example, this is the expression that you find. The other things that you see, d over lambda is smaller, and the array gain is smaller. So if the frequency is higher, sorry, if the frequency is smaller, the wavelength is higher, the ratio d su lambda is smaller, and the array gain is smaller. On the right, you have two curves for two different pointing direction. So we steer the beam at 0 degrees or 20 degrees, and we plot as a function of d su lambda, d over lambda, with d over lambda that varies from 0 to 1. So as you can see, when d over lambda increases, the array gain increases. And I mean, this increase is different depending on the pointing direction. And we have also this behavior on the border, but it's irrelevant. This is another example where instead of, I mean, we increase the number of sensors for 20 to 100. So obviously the array gain is higher, but we have a similar behavior as before. So if d over lambda is 0.5, it is constant. If it's 0.2 is smaller. And then we have this different behavior depending on the value of theta t. Actually, if, I mean, d over lambda is 0.5, the two curves should coincide, I mean, here and here, because if d over lambda is 0.5, the value should not depend on theta t. So the two curves should intersect in 0.5. Okay. Let's see the array gain of the optimum beamformer, and then we analyze some numerical cases. Okay. Now, this is the array gain for a given h, and actually we have already derived the expression of the optimal beamformer. So the beamformer that maximizes the output signal-to-noise ratio, and we prove that to maximize the output signal-to-noise ratio is equivalent to maximize the array gain. Actually, you can rederive exactly the same result in a different manner. So we can set the problem as the problem of maximizing the array gain with respect to h, subject to the constraint that the energy of the beamformer is, for example, equal to 1. So we constrain the energy of h, and subject to this constraint, we maximize the array gain. We can solve this problem by using the Schwartz inequality. There are different forms of Schwartz inequality, and we can apply one of that. So the modulo square of the product of these two matrices, so we can express H Hermitian A as H Hermitian Q square root of Q multiplies by the square root of the inverse of Q. I mean, the product of these two is the identity matrix. So if you apply the Schwarz inequality, the modulo square of the product of these two vectors, this one and this one, is smaller or equal than the product of the Euclidean norm square of these two vectors. And equality, so this term here is always smaller or equal than this, and equality is obtained only when these two vectors are collinear. So the maximum of the numerator is achieved when the two vectors are collinear. Now, this modulo square here is equal to this. This modulo, sorry, not modulo, Euclidean norm square of this is equal to this. The Euclidean norm square of this is equal to this. Then you simplify this and you get this. So in other words, the maximum achievable array gain, so the maximum value of this quantity, so the maximum value of this quantity is this one, and it can be achieved when these two vectors are collinear. Vector collinear means that one is a scaled version with a constant scalar factor k of this. So if you multiply by q to minus 1/2 on the left, you find that the optimal beamformer is proportional to q to minus 1a, which is exactly the white matched filter that we already derived, if you remember. So it's not a different solution, it's just a different way to find the same solution. So the optimal clairvoyant beamformer has this expression here, so it's proportional to the inverse of the normalized partial correlation matrix that multiplies the array response calculated at the direction arrival of the suits. We choose the constant as 1/n. So when Q is the density matrix, so when the noise is partially white, the optimal beamformer coincides with the classical beamformer. The array gain of the optimal beamformer, we prove, is this one, and can be expressed as the trace of the inverse of Q multiplied by A. So in summary, this is the array gain of the optimal beamformer. This is the array gain of the classical beamformer, and obviously the term on the right is always smaller or equal than the term of on the left. And equality, we have equality, so the two are equal only when the noise is partially white, so when Q is equal to 1. So the classical beamformer is optimal only if the noise is partially white. And in that case, the two array gain coincides, and both of them are equal to the number of sensors. Otherwise, they are different, and the array gain depends on the structure of the correlation. So it depends on Q. So let's see some numerical examples. Okay, and let's compare the array gain of the optimal clairvoyant beamformer with the array gain of the classical beamformer. Now let's assume we have a standard EULA composed by 20 sensors. Let's assume that the noise is correlated, and the correlation can be modeled as an autoregressive process of order 1. So the elements of the normalized partial correlation matrix are rho elevated to the modulo of the distance between the position of the elements. So the correlation decays exponentially, and the speed of decay is controlled by this parameter rho. Rho is the correlation coefficient between adjacent samples. So when the difference I minus k is equal to 1. So rho is the spatial one-leg correlation coefficient. Let's assume that there is only correlated noise and there is no white thermal noise, there are no jammers, okay? And let's calculate the array gain of the optimal beamformer, which is given by this expression, and the array gain of the classical beamformer that is given by this expression. So we have to calculate this trace and this trace. MATLAB is very simple. So for example, let's assume that rho is 0.9. If rho is 0.9, it means that the power of the noise is not uniformly distributed in angle, but is concentrated around the vertical. So it's a sort of low pass process, but low pass in the angle domain. And so the array gain is somehow inversely proportional to the spatial power spectral density. So the spatial power spectral density has a peak in theta 0, the array gain as a whole in theta equal to 0. So that's why the array gain decreases when we get closer to 0. Because when the angle decreases, so when we point the beam at smaller and smaller angles, more noise enter in the beamformer because the power spectral density increases. The power spectral density of the noise increases. The other thing that you can observe is that the array gain of the optimal beamformer is always greater than the array gain of the classical beamformer. So the hole in the array gain is narrower, which is better, obviously. The narrower it is, and the better it is. And the difference is not significant, but I mean, there is some difference. We can also plot, for example, the array gain by setting the steering direction of the beam and changing the value of the correlation coefficient from negative to positive. And we see that we see this result. And I mean, what is important to observe is that, as expected, the optimal beamformer is an array gain that is always greater than the one of the classical beamformer. But for these values of the parameter, the difference is not very large. I mean, the difference becomes larger when rho tends to -1 or 2 + 1. But otherwise, if rho is small, basically there is no difference. So if the correlation is not too large, basically from the point of view of output signal to noise ratio, there is not a huge difference in performance between the classical beamformer and the optimal beamformer. Remember that in practice, you cannot implement the optimal beamformer. You have to replace the covariance matrix with a sample matrix estimator. So you have to implement an adaptive version, and the moment you implement an adaptive beamformer, you have what we call adaptivity losses. So you have some loss. So it makes sense to use an adaptive beamformer if the difference between the two is significant. Otherwise, it's better to use the classical beamformer. So these are other curves for different values of the parameter. If rho is smaller, the peak and the power spectral density is less pronounced, and so also the hole in the array gain is less pronounced. In this case, this is the case where the correlation is extremely large. So in the case where the correlation is extremely large, you can observe a significant difference between the optimal beamformer and the classical beamformer. This oscillating behavior is due to the side lobe of the classical beamformer that are very pronounced. So, but the message is that that it can be worth implementing the optimal beamformer in an adaptive manner if the difference between the optimal beamformer and the classical beamformer in terms of array gain is significant. Otherwise, because you have to take into account also the adaptivity loss. Otherwise, it's better to forget the correlation, don't take it into account, and implement the classical non-adaptive beamformer. The last numerical example, and then I will send you the MATLAB code, and so you can play with it. The last numerical example is the following. In the previous example, there was only correlated noise. In this example, we have white noise and a number nj of directional jammers. So it's a different example because the disturbance has a different structure. In the previous example, we compare the two array gain when the noise is correlated and there are no jammers, no directional interference. In this example, we have the classical thermal noise, which is white. And in addition to that, we have a given number, nj, of directional interference, so jammers. So the correlation matrix or covariance is the same because the disturbance is zero mean. The disturbance covariance matrix Rw is given by the sum of the covariance matrices of the nj jammers, and these are all rank 1 matrices. So sigma jk square is the power of the k jammer coming from this directional arrival, theta jk, and this is white noise. So the total disturbance, sigma w square, is the sum of the powers of the jammer plus the power of the noise. So the covariance matrix Rw can be expressed as the total power of the disturbance that multiplies the normalized correlation matrix Q. So if you put this in evidence, you have to divide by this. Q is given by this expression, and you can express this coefficient here and here in terms of the jammer to noise ratio for the K jammer. So this is, so remember, sigma W square is this one. So if you divide numerator and the denominator by the noise power, this coefficient here is the jammer to noise ratio of the kth source divided by J and Ri, the summation of all of them, plus 1. Here you have 1 divided by the same summation. So this is Q. So as you can see, Q depends on the value of the jammer to noise ratio. Depending on the value of J and R, you give more emphasis to this matrix or this matrix. So the array gain depends on the jammer to noise ratios, on the values of the jammer to noise ratio. and obviously their directional arrival. So then we plug this here and here, and we calculate the array gain. So this is a first example. So here we plot the array gain for the classical beamformer and the optimal beamformer under the assumption that there are two interferences coming from angle minus 45 degrees and 45 degrees. And the interference to noise ratio for the first interference is 0 dB. For the second is larger, is 6 dB. If you plot the array gain, this is what you get. So how can we, what can we observe? So the array gain is above 20 dB, except close to the angle that correspond to the directional arrival of the two interferences, minus 45 and 45. It's clear that when you steer the beam in the direction of one interference, you don't cancel the interference. And so our ability to reject the disturbance is limited. So the array gain is limited. So that's why we have a hole in the array gain in correspondence of the directional arrival of the two interferences. Then the second hole is deeper. Why? Because the second jammer is more powerful. That's why, this is the reason. The other thing that we can observe is that the classical beamformer has worse performance because the array gain is always smaller. The array gain of the classical beamformer, the blue curve, is always smaller than the green curve, which is the array gain of the optimal beamformer. And the fact that the hole is narrower, the optimal beamformer is narrower, it's a very positive fact, and it says that basically we can detect sources that come from an angle that is not far from the angle of the jammer. If you use the classical beamformer, the blind sector, the interval of angle on which we cannot reveal the presence of a source because the array gain is small, is larger. So the narrower is this and the better it is. And then the optimal beamformer does not have the oscillating behavior that the non-adaptive classical beamformer has because of the presence of side lobes in the beam pattern. In this other figure, we assume to have only one jammer coming from directional arrival 0 degrees, so theta 1 is 0 degrees. And we plot different curves, assuming different values for the jammer to noise ratio. Now, obviously, we have a hole at 0 degrees, and the value of the horizontal level is different. And you can notice that when the jammer to noise ratio increases, the array gain increases. Why? You have to understand that this figure basically assumes that the total power of the noise is kept constant. So when we assume that the jammer to noise ratio is greater, so it goes from 0 to 6, from 6 to 12, and then to 18. So when JNR increases, to keep constant the total power of the noise, of the disturbance, if the power of the jammer increases, the power of the white noise should decrease. And if the power of the noise decreases, basically when you point the beam far from the direction from which the jammer is coming, at the output of the beamformer, you have only noise. And if the noise power is smaller, the array gain is better. So when J and R increases, the level of the white noise power decreases, so the array gain increases. So this is the reason why things gets better if J and R increases. So in other words, it's better to have a directional disturbance than white disturbance, because okay, the directional disturbance does not allow you to detect the presence of a signal of interest from that direction and in a sector around that direction. But outside that, if you point the beam far enough from the directional arrival of the interference, you can achieve better performance than if the noise is uniformly distributed in angle. And in that case, I mean, whatever is the pointing of the beam pattern, you will find some noise that passes through the beamformer. So this is more or less the explanation of the results in these curves. The last numerical example, and then I send you all the MATLAB code. The last numerical example is the following. Badri, can you hear me?
Yes, sir.
Can we make 2 minutes break? I go to the restroom. And then I describe the last case study, okay?
Okay, sir.
Just 2-3 minutes. Okay, so I want to describe the last numerical example. And then I will send you the MATLAB code, all the MATLAB code for all the results that you have seen. So you can derive the same results. So let's assume that we observe signal plus disturbance. The disturbance is made by interference and white noise. So the total disturbance is called W of n. Then let's assume that the signal is a single point-like signal. So it has the usual structure. The interference is also directional. So it comes from direction theta j, and the signal generated by the source of interference is Sj of n. Then let's assume that the array is Euler, so the array response is this structure. The other assumption is that the signal is a wide Gaussian process. So the signal generated by the source is a sequence of independent and identically distributed complex Gaussian random variables with zero mean and some power sigma square. So the signal is temporally uncorrelated. The jammer has the same distribution. So the jammer comes from a different direction. So it is spatially correlated, but temporally wide. So in time, it's a sequence of independent and identically distributed complex Gaussian random variables with zero mean and some power sigma j. The noise is white. It is temporally white and spatially white. And so the spatial correlation matrix is the identity matrix. And so it means that the snapshots are identically distributed, mutually independent, the various snapshots, and each snapshot has a joint probability density function that can be modeled as a complex Gaussian vector with zero mean vector and covariance matrix Ry, where Ry is the sum of the covariance matrix of the signal plus the covariance matrix of the disturbance. And this is the covariance matrix of the signal. This is the covariance matrix of the disturbance. The disturbance is jammer plus noise. So the total disturbance power sigma w squared is the power of the jammer plus the power of the noise. Then we can define the signal-to-noise ratio in the usual way. So it's the power of the signal divided by the power of the noise. This is clearly the signal-to-noise ratio at the input of the beamformer. Then we can define the signal-to-jammer ratio and the jammer-to-noise ratio. Okay. So the spatial covariance matrix of the disturbance is the covariance matrix of the jammer, which is directional, plus the covariance matrix of the noise, which is white. And then again, we put in evidence the total power of the disturbance. So what remains in brackets is the normalized spatial covariance matrix of the disturbance, and it is given by the spatial covariance matrix of the jammer plus the spatial covariance matrix of the white noise. So the terms in brackets is the normalized spatial covariance matrix of the total disturbance, and it depends on J and R. We want to compare the classical beamformer and the optimum beamformer, and also Capon as tools to estimate the spatial power spectral density. So this is the beamformer output in general. The average power is the modulo square of the output of the beamformer average with respect to time. So the summation goes from 0 to n minus 1. So we average over the different snapshot. And you can replace YF with its expression. So this is the definition of the output power for a generic beamformer H. So then you can calculate this either for the beamformer, for the clairvoyant beamformer, which can be defined this way, 1 over m q2 minus 1 a of theta, or the classical beamformer, which is the matched filter. So this is the matched filter, and this other is the white and matched filter. And so if you plug these two H here, you find an estimate of the power by using the optimum or the classical beamformer. Then remember, to obtain the spatial power spectral density, you should take the output power and divide by the filter bandwidth. Now, roughly speaking, the bandwidth of the filter is on the order of the reciprocal of the length. The length is m, so you can find the spatial power spectral density estimate by multiplying by the filter length. And this is for the optimal beamformer and for the classical beamformer. Okay, so this is an estimate of the power spectral density and the by using the optimal beamformer. This one below that you know very well is the estimate of the spatial power spectral density by using the classical beamformer. So this is clairvoyant because Q is unknown. This other does not require to estimate Q, but just make use of an estimate of the data covariance matrix, and so it makes use of the sample correlation matrix. And then we have Capon. So if you remember, this is the impulse response of Capon beamformer, and this is the expression of the spatial power spectral density estimate obtained by using the Capon beamformer. So notice the difference between Capon and the classical beamformer. So with Capon, this term is at the denominator, but instead of R hat, we have the inverse of R hat. And it is exactly this operation that makes Capon more selective than the classical beamformer. So it has better resolution. So we want to compare, in summary, these three methods: the clairvoyant optimum beamformer, the classical beamformer, and because the array is EULA, it can be implemented by using the FFT, you will see in the MATLAB code, and the adaptive Capon beamformer. And we want to compare them for different values of the parameter to understand their property better. We are assuming that the signal of interest is present in all the temporal snapshots. So we don't have signal-free secondary data vector that can be used to estimate separately the disturbance covariance matrix. So the adaptive beamformer that we implement is the Capon beamformer. Okay. These are the setting of the parameters. Remember that in order to be able to invert the sample covariance matrix, the sample covariance matrix should be full rank. So the number of snapshots should be at least equal to the number of sensors. So the minimum number of snapshots is 16. So if M is 16, you cannot implement Capon if N is smaller than 16. So that's why we start by setting the number of snapshots equal to the minimum value that allows you to implement Capon. So you can see Capon is very selective. So, sorry, I forgot to say. We assume that in the data there is a signal coming from 10 degrees, a jammer coming from minus 20 degrees. The signal to noise ratio is 30 dB, and the signal to jammer ratio is 10 dB. So the power of the signal is 10 times greater than the jammer. The noise power is 1. So as you can see, the classical beamformer, the red one, it cannot discriminate between what is jammer and what is signal. But for the classical beamformer, it just measures the power coming from a specific direction. So it treats the jammer exactly the same way as the signal. So he has two peaks. One is covered, but is there. So he has two peaks, and the difference between the height of the peaks is the 10 dB, which is the difference between the signal power and the jammer power. And even Capon is not able to estimate separately the covariance matrix of the disturbance. So it doesn't know what is signal, what is disturbance. Capon, in a different manner, estimate the distribution of the power in angle. And I mean, the shape of Capon is not, I mean, nice, because N is very small. So the quality of the inverse of the sample covariance matrix is bad. The optimum beamformer knows exactly what is the matrix Q. So the optimum beamformer knows this matrix here and knows that from this direction there is a jammer coming. So he is a clairvoyant. He knows that what we observe from this direction is jammer, is not signal. So the calculation of the inverse of Q has the effect to create a hole in the optimum beamformer estimate at the direction minus 20 dB, which is the direction where the jammer is coming from. So the optimum beamformer, clairvoyant, has a peak only in correspondence of the directional arrival of the signal of interest. If N is greater, you see that the behavior of Capon is more regular, and we have the two very high peaks in correspondence of the two signals, signal of interest and jammer, and again, the optimum beamformer as a whole at minus 20 dB. So, I mean, the fact that Q is perfectly a priori known, and we calculate the inverse of Q, is the reason why we have a hole. So it's the reason why the optimum beamformer is able to cancel the jammer. the classical beamformer and K-form beamformer, they just basically estimate the level of power for different angles, and they don't discriminate with signal of interest and jammer. So different values of the parameter you see. In this case, for example, if the signal to jammer ratio is 0 dB, it means that the power of the signal and the power of the jammer is the same. So the classical beamformer has two peaks with the same age. So you can observe that the resolution of Capon is much better than the classical beamformer. These are other examples. Here, we change the value of the signal to noise ratio. Here we increase M, so all the main lobes became narrower. And so these are, some final, very brief final remarks. Now, the clairvoyant beamformer make use of a priori knowledge of the noise covariance matrix Q. This matrix obviously is unknown, and so the performance of the clairvoyant optimal beamformer should be considered as a benchmark to which an adaptive beamformer should tend. And we have seen different adaptive beamformer, sample matrix inversion beamformer, loaded sample matrix inversion beamformer, Capon, generalized side lobe canceller, and so on. So they should tend, when the number of snapshots increases, to the performance of the clairvoyant optimal beamformer. So the performance of it should be considered as a benchmark. Any adaptive beamformer in practice has to replace the unknown disturbance covariance matrix Q with an estimate. Sometimes we don't have available secondary data vector that contains only disturbance, so we cannot estimate Q. We can only estimate RY. So it is like if we have our data contaminated by the signal. In this case, the adaptive beamformer that we obtain is called Capon, or minimum variance distortionless response. And asymptotically, the performance are the same as in the case where we have secondary data free of signal, but only asymptotical. But the convergence to asymptotical performance is lower because of the contamination of the signal, because of the presence of the signal. So if it is possible, it's better to estimate separately the disturbance covariance matrix without the contamination of the signal. If it is not possible, okay, and we do what we can, obviously. The EULA classical beamformer can be implemented in a very efficient manner by using the fast Fourier transform, and it is not adaptive, and it does not require a priori knowledge of Q. So it's a good choice if you don't want to spend more computational complexity and you don't want to make the beamformer adaptive, because obviously the computational complexity increases. Then we have seen that the array gain of the classical beamformer and the optimal beamformer in general depends on the structure of the noise partial covariance matrix Q. And if Q is not the identity matrix, it depends on also on the direction arrival of the source. So depending which is the direction arrival, the array gain can change. classical beamformer and optimal beamformer coincide, so they are exactly the same and they have the same performance only if Q is equal to the identity matrix. So only if the noise is partially wide. In general, the optimal beamformer outperforms the classical beamformer. But depending on the amount of correlation, the difference can be negligible. And so, I mean, you have to think carefully whether it is worth or not to use an adaptive beamformer. Sometimes it's better to use the suboptimal classical beamformer, which for sure avoids the adaptivity loss and which has some robustness that we have investigated. The weakness of the classical beamformer, we understood very well, is the resolution. The resolution of the classical beamformer is limited by the number of sensors, and actually it is the reciprocal of the number of sensors. And this is called Rayleigh resolution. Capon, which is an adaptive method, has always better resolution than the classical beamformer. But if you want to achieve the best possible resolution, you have to use a super resolution method. So a model-based method. We have seen, for example, nonlinearly square, deterministic maximum likelihood, stochastic maximum likelihood, but the complexity of these three is very large. So in alternative, you can use spatial Uli-Walker that I did not describe in detail, but can be found in the view graph. Or you can use music and Esprit, and there are many others. But I can say that root music is a very good option if the array is Euler. Esprit is a very widely adopted method for non-Euler arrays that has this property that can be split into identical subarrays. So Esprit has performance very close to optimal with the limited computational complexity. The only constraint is that you should be able to separate the array, to split the array into identical subarray. This is the only constraint. Okay. I think we can stop here. And now I send you the MATLAB code. I think the only code that I've not sent is this one concerning chapter 6 and chapter 7.
Yes, I received it and I forwarded for participants.
Okay, just this chapter are shorter. So basically, you can find the 5 classical optimum Capon beamformers is the MATLAB code used to derive the last example that I described. And the previous one is the MATLAB code to derive the array gain in the presence of jumbo. Let me check. Yes. So these two figures have been derived by using this file, which is called Array Gain, White Noise, and Jamming. I mean, from the name of the file, you can understand. And then if you run, if you run, you can find immediately which figures have been derived with this program. So I think when you study this topic, it can be useful to use this MATLAB code. You run the code, you change the parameters, you check how the output changes, so you can understand better the role of the various parameters. And this is very useful to understand the algorithms, obviously.